All right, so I just want to run through the different module stuff. Um, all right, here's what you're going to see in your B1 module. The first thing is identifying functions from relations, and this is the type of question that it would look like. So, all right. Um, the main thing you need to know about a function is that if I give a function an input, so like what is, oh, let me turn my pen. Ooh, I might need to charge it. Yikes. So if I have like a function and I input 3, it needs to be one single number as an output. The thing that is currently on screen, so relation 1, if I input z, I don't know if my function is going to return -8 or if it's going to return -5. That's not a function. Sometimes we say that this is a 1 to 2, and functions are not 1 to 2. Okay. Um, they can be 2 to 1, and I'm sure we'll see an example of that, where the same input, so like f of 1 could be 1, f of -1 could be 1. There's two different values that return the same value. For example, the absolute value function does that, and that's okay. It's still a function. But we need one specific output for every input. So the thing on screen is not a function. It's just a relation. Here, this is also not a function. For one single input E, we have all these different outputs. Okay, here this is a function. So no matter what you input, whether it's the letter U or the letter F, or the letter Z or E or C, you always get the same output, which is the word sky. And that's fine. So this would be a so-called 5 to 1 function because there's 5 different inputs that give you the same output. That's fine. Functions are 2-1. Okay, so I don't care how many different things give you the same output. You just can't split from the beginning, right? So relation 3, that's a function. Oh, try again. My goodness. All right. Relation 4, we just want to see, so like, notice how -5 repeats itself on the input list, and it has two different outputs. So I don't know if f of -5 is going to equal -7 or if it's going to equal -9. That's not a function because I have that ambiguity. The same input gives me different outputs. Okay, so not a function. And I guess that's it for that kind of thing. So go ahead and check, get the green check mark going. There it is, correct. Okay, cool. So that's one type of question that we'll see. What else is on the domain thing? So, aha, this is also called a vertical line test. All right, the whole idea with vertical line test, it's the graphical version of what I just said. So, you can see this graph is a parabola, and no matter where you draw a vertical line on that graph, it'll only intersect this curve at one spot. That's a function, okay? The reason it's the same idea as what I said before is what you input are x values, right? So the fact that when I input an x value, I look up and I'm only going to hit my graph at one spot. That's because there's one output for every input. No matter where I stand on my x-axis, I look up, I'll only hit my function at one spot. Here's an example of something that's not a function. So if here's my x-axis and I look up, I'll hit, 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 not a function. I don't know what my output is. There's 3 to choose from. So anyway, graph 1, that's a function. Graph 2, this is also a function. So these solid dots are where our function is defined. So this lower left dot, it looks like it's -2, -1 is its coordinates. And it goes over, and then we have an open dot, and then a solid dot. And then this goes over open dot. And it looks like the x value here is -1. And so what is f? I'll write it like this. What is my function at -1? It's 0. Okay, this is not ambiguous at all. An open dot like this is not included. I'm looking up to this dot. And so if you look at my graph over here, this dot has the coordinates -1, 0, and my function is 0 at -1. Graph 2 is a function, passes the vertical line test. Graph 3, not a function. Do you see the two dots in the lower left-hand side? You have two stacked dots, right? I sort of have this type of scatter pattern here. Okay. These two stacked dots, they have the same y value. They're not saying they have the same x value, but different y values. I don't know if f of -2, that's the x value, right? I don't know if it's going to be -2, which is this higher dot, or if it's going to be -3. And since I don't know, since it's ambiguous, it's not a function. Graph 4 is a function. You can see any vertical line only hits at one spot. Graph 5, not a function. Okay, if I draw a vertical line at 4, I'm going to hit at two different spots, right? So I come in, boom, boom. I'm going to hit at two spots, not a function. This is something like x equals absolute value of y. It got shifted around a bit, but it's something kind of like that. Anyway, it's not a function. Okay, so that should do it for that one. And we got that, correct mark. So cool. Let's go back to the question list. All right, evaluating functions, absolute value, rational, radical. Okay, fine. Let's see what that looks like. Okay, so can we evaluate functions? Okay, f is an absolute value function, and we have that. So f of x is equal to the absolute value of 6 times x minus 5. Okay, so if I plug in a half, or sorry, if I plug in negative a half, then 6 times negative a half is -3. So I have -3, but I want the absolute value of that, -5. So this is +3 minus 5. This is -2. Okay, so that's what f of -1/2 is. It's -2. G of 5 is 5 divided by 5 plus 5 squared. This is 5 divided by 30 because 5 squared is 25, and I add it, and that's 1/6. Okay. What else? What else? We have h. H of 4 is the square root of -2 times 4 plus 10. So that's the square root of -8 plus 10, which is the square root of 2. Okay, so that's what I want to input. Let me flip this around and do that really quick. Um, Although, I don't know, maybe you can just trust me and then we can just move on. But just in case you don't trust me, let's do it. So we got -2. Here we've got 1/6. And here we've got the square root of 2. Great, there we go. All right, let's keep this going. Domain and range of ordered pairs. Okay, so now we're getting domain and range. So domain, it's all the possible inputs, and the range is all the possible outputs. So this function t, or I guess this relation t, um, it, it'd be weird to draw a graph of it because we have letters as well. But if it was all just numbers, its graph would look like a bunch of discrete points, right? But it's still a valid function, or I should say relation. So give the domain and range of t. Okay, so whenever we have ordered pairs, we have xy pairs, this first entry is telling us things in the domain. So in the domain, the way we give this answer, the way we write this list, don't know why. It's acting up a little bit. Let's try this again. Maybe my pen finally died. Let's do it, okay? So we need to use set notations. That's these curly brackets. And then we just list out all the different things we see in x values. So I see 5, I see n, I see 0, I see 8. Those are all my different x values. What are all the different y values that I see? I also see 5. I also see 8. I see m, and I also see n. And that's it. That's domain and range. X values, y values. Okay. Domain and range gets more interesting when you start to have graphs. So you have domain of a square root function. I say graphs, but also algebraic equations. So here's the thing. In this class, we only deal with so-called real numbers. And that's a terrible name because they're just as real and just as imaginary as any other number. Numbers are all just made up. But with real numbers, you cannot take the square root of a negative. Okay. The square root, oh, my pen finally died. To be continued. Let's get my share to come up. Let's pause. Okay, cool. I got my pen plugged back in. So with real numbers, the square root of -1 does not exist. Okay. It's not a real number. Now, if that seems weird, let me talk about some other number distinctions. For example, if I were to say we only cared about integers, or so-called whole numbers, these are things like -2, -1, 0, 1, 2, and so on, right? I would say 1/2 is not an integer. Okay, I'm not trying to say anything deep here. All I'm trying to say is there's some notion of numbers which are named. This is another valid number. It just doesn't live in that set. Same idea here. The square root of -1, it's a totally valid number. We sometimes call it I. It's just not a real number, which is it's a stupid name. I hate the name real number. I don't have a better name, right? I kind of want to call them one-dimensional numbers, but even that's not, I don't know. Um, a good name for these might be like length numbers. That might be a good name for it because these correspond to lengths. And then these, instead of imaginary, I would kind of wish they were called rotational numbers. Rotational numbers. We don't get into it in this rotation, whatever. Ro who cares? I'm writing terribly anyway. I guess okay. Rotational. My God, numbers. We don't get into it in this class, but to multiply by I just rotates. Okay, look, if I were to draw, I can't help myself. I'm sorry, guys. Here's 0 and here's 1. If I multiply 1 by 2 times 2, it sort of stretches it out to be twice the length, and I'm over here at 2, right? But if instead I multiplied 1 by I, it rotates it by 90 degrees, and now I'm up here at I. And if I multiply by I again, I rotate by another 90 degrees, and I'm over here at -1, and that's why I squared is equal to -1. Because if you turn 90 degrees and you turn 90 degrees again, you've turned 180 degrees. These numbers rotate, okay? Anyway, imaginary numbers are valid numbers. They're just sort of like movement E, whereas real numbers are length E. And the square root of -1, it's not a length, it's a rotation. If you want, whatever this mysterious number is, let's call it x, what needs to be true is that if I perform x twice, if I do x times x, I land at -1. And it's true that if I rotate by 90 degrees and rotate by 90 again, I'm back at -1, right? Anyway, whatever. Sorry for that tangent. The point is, square root of something negative, this thing is not real. Again, terrible name. It's not a length. Okay, it doesn't exist as a length. So, what am I taking the square root of? Taking the square root of x plus 3. In order for this to be defined as a real number, we need the inside, which happens to be x plus 3, to be bigger than or equal to 0. Okay, it's not allowed to be negative. It can be 0 or it can be bigger. So what does this mean as far as x goes? So we got to get the x by itself. It means x is bigger or equal to -3. And that is the domain. Okay. We'll do a couple of these. I think they're all going to be just as simple as this. It'll just be x plus or minus something to move it over. So maybe I'll come up with one a little bit more complicated. Write your answer in interval notation. Okay, fine. That's the wrong interval. Let's undo this. That's the right interval. Why is that the right interval? Because you're allowed to be 0. That's fine. And then you can go up as high as you want, up to infinity. So there we go. Check. Try again. Oh, sorry. What does x need to be bigger than? It needs to be bigger than -3. Sorry. We need to be bigger than -3, but we could equal -3. If you plug in -3, you'll have f of -3 is the square root of 0, which is 0. That's totally fine. Okay. All right. That's why I had 0 on the mind. Sorry about that. Okay, let's try another. Let's see if it gets any harder. Okay. No harder. We just have to realize only x is in the square root. And so here we can go from 0 to infinity because the square root of x minus 6, this is the part that has restrictions. The thing inside the square root, which is just x, has to be bigger or equal to 0. Oh, okay. So we need to be bigger or equal to 0. That's all this is saying. Let's look at another one. Same idea. Yeah, here we need to be bigger or equal to 5. So x minus 5 is underneath the square root. And what we need is the stuff under the square root, so I copy and paste the whole thing, is bigger than or equal to 0. So what does that mean about x? It means x is bigger or equal to 5. Okay, so that's what I would put here. Do this, and do I click that button? No. Do I? Let's roll keyboard out. 5 over infinity. Check. There you go. Okay, so that's good enough with those. I could show you something more interesting. We're after three relation. Sure. Okay, I will talk a little bit more about the square root function. before we use the next problem. Suppose I had something like the square root of 2x minus 8. Well, in order for this to be defined, I take everything underneath the square root, 2x minus 8, and I set that to be greater or equal to 0, and then I see what it says about x, right? So if I move over the 8, I have 2x is greater or equal to 8. I divide by 2, I have x is greater or equal to 4. So that's my domain in this case, right? If I had something really sneaky, like say x squared minus 3, well, now it starts to get a little bit weird, but it's the same process. You take everything underneath the square root and say this has to be bigger than or equal to 0, and then you see what it says about x. And so in this case, it's going to say that x squared is bigger or equal to 3. And when you take a square root, or I think it's really best if you just kind of draw the picture of x squared minus 3, x squared minus 3 looks like this. And so we need this thing, which if we think of it as the y value, we need it to be bigger than 0. So that's over here and over here. That's when x is bigger than, well, I guess it's sort of, okay, if I want to, I'll do this side first. It's when x is more negative than negative root 3. And it's when x is more positive than positive root 3. That's what's going on here. Anyway, we don't have any of that complicated. I didn't do any of the advanced domain problems, at least not that I know of right now. We'll do the problem on screen. All right, domain and range from a discrete graph. The x values are domain, the y values are range. So what values do we see as x values of these dots? That's all we have to do. I see a -1. I see a +1. I see a +3 and a +4. Those are the different x values of these dots. What values do we see as y values? I'm going to go from bottom to top, and at the very bottom, I see a -4. I see a 0, +1, and +4. Okay, that's it. That's all this wants. Okay. All right, finally, domain and range. Sure, let's do this one, and then we're going to be done with the B1 module. All right, so what are the different x values that, if you were to draw a vertical line, you would hit your graph? And importantly, you would not hit your graph when x is -3. So if x is -3, if you draw that vertical line, you're going to hit this open circle, but the open circle is not part of your graph. We draw it because we're letting you know you can get as close as you want to -3, but you can't touch it. So that just means we have this open interval. I go from -3 up to, and I have an open circle at 2. That whole range on the x-axis, anywhere I draw a line, I'll hit my function. And so that's my, I said range on the x-axis, and then of course range refers to y-axis. Hopefully you know what I mean. That interval on the x-axis is my domain. Okay, range. How low do we go? It looks to me like that curve genuinely hits where y is -5. Okay, we truly hit that. Whereas if you follow the curve up, we do not hit the highest point, which looks like y equals 4. So I do hit the lowest point, and I do not hit the highest point. It's a closed on the left interval. I do hit -5, and I do not hit +4. There we go. That's it. All right, so that's your B1 module. And we got some time. Let's go ahead and knock out B2 while we're at it. Okay. B2 is a bit bigger, 13 topics. Ooh, we'll see. How long is this video so far? I don't know. All right, solving an equation written in factored form. Wonderful. Let's do it. Solve law. Okay, so here's what you need to know. If I have two numbers, a and b, and I multiply them, and they equal 0, this implies that a equals 0 or b equals 0. The only way you can multiply two numbers and get 0 is if at least one of them is 0. And there's nothing special about two numbers. This is true for three numbers and four numbers. If you multiply numbers and get 0, at least one of them is 0. So the fact that -2, which, by the way, is not 0, times v plus 3 times minus v plus 1 is equal to 0 means at least one of these things is 0. Now, this one's never going to be 0. So what really matters is either v plus 3 equals 0 or minus v plus 1 equals 0. This is playing the role of A, and this is playing the role of B, right? Okay, so what does this mean? This would mean that v is -3. And what does this mean? Oops. This would mean that v is 1. So those are my two solutions. Either v is 1 or v is -3. Yes. Term. Will I? Senses my finger. There we go. So either, we'll just do -3 first, doesn't really matter, or 1. Check. There you go. We'll try another. Right, so we're just going to take these binomials that are in parentheses. So 4 plus u and 4u minus 5. And then independently, each of them we set equal to 0. So 4 plus u equals 0 says u is equal to -4. And 4u minus 5 equals 0 says, okay, we'll go in 2 steps. So 4u has to be +5. And if I divide by 4, that says u had better be 5 divided by 4. So these are my two possible solutions, -4 and 5/4. I'm not going to enter it. So that's what's going on there. Okay, combining functions to write a new function that models a real-world situation. Let's take a peek. A car rental company charges an initial fee plus an additional fee per mile driven. Fine. The charge depends on the type of car, economy or luxury. The economy charge to rent an economy car is given by this function. Fine. Okay, so E is equal to 14.95 plus 70 cents a mile, where M is the number of miles driven. Right. The luxury car is 21.4 plus $1.25 a mile. Okay, fine. Let's see how much it costs to rent, oh, how much more it costs to rent a luxury car than an economy car. So my luxury cost minus my economy cost, that difference is how much more it costs to rent a luxury car. And so we can just go through. I can say, okay, 21.4 minus 14.95, 21.4 minus 14.95. Gross, we'll make that a 0, and we'll make this, what do we do here? Oh, how would I actually do this? I would think to myself that if I add 5 cents, I'll get up to 15. Then I need $6 in order to get to 21. And I need 40 more cents. So six, yeah, 6.45. Okay, fine. That seems right. And 1.25 minus 0.7. 3 is 0.55. Okay, so 0.55. So this difference is 6.45 plus 0.55 m. This difference is how much more it costs to rent a luxury car than an economy car. Um, so anyway, I didn't enter that here. I kind of don't want to. Let's just see what other types of stuff we might have to do. Okay. This is the exact same type of question. So the luxury car is more expensive than the economy, and we want to know how much more does it cost to rent a luxury car than an economy car. Let's try another. Are they all the same? Are they all just subtraction? The total amount saved using both plans combined. So this will be addition, right? Both plans combined. That sounds like I add stuff. Amy will initially set aside $250 and then add $165 every month to the savings. Fine. And then they give you that as a function. Her husband will not initially set any amount aside, but he will add $5.95 to the savings every month. So then we're that. So then if you add these two things, the total amount in savings, the total amount is what Amy initially added, which is $250, plus the amount she adds every month, plus the amount her husband adds every month. And then we can combine these two because they're both multiples of n. So this is 250 plus, let's see, 5 and 5. That makes this 600. So then that'll become 760. Okay. All right, whatever. Seems like these problems are either going to be adding or subtracting. So we can do that in order to model the real world. Sure, why not? Variable expressions as inputs of functions. Okay, wonderful. This is one of the areas that it seemed like people struggled on with the last test. So I'm glad that we're talking about it. What f does to its input is it squares it multiplies it by 4, and then it takes away 6 it does all this, right? So it doesn't matter what I input. So if what I input is x plus 7, then I have to do x plus 7 squared, x plus 7 here. And now in some sense, this is done. This is what f of x plus 7 is, but they don't want you to write that. They want you to actually FOIL and figure out what this is. So now if I have something like this, to square something means you multiply it by itself. So what this means is I have a plus b times a plus b. And now if you know the term FOIL, you can also draw a picture of this. So to square something, you should draw a square. You can imagine that this length is a and this length is b. So the total length is a plus b. And so then similarly, this length is a and this length is b. And so that total length is a plus b. And when I square it, I'll get the area. And this area is composed of an a squared, an ab, a b squared, and an ab. And so the total area, when you add them all up, what you get is a squared plus 2ab's plus b squared. And you could also think of it as foiling, where you sort of just, distribute all over the place. But okay, so we have x plus 7 squared. So x is playing the role of a, 7 is playing the role of b. And so I get x squared plus 2 times 7 times x, which is 14x, plus 7 squared, which is 49. So I have x squared plus, let's do some other stuff. This is a minus 4x and a minus 28. Minus 28 minus 6 is minus 34. Okay, so I have 14 x's minus 4 x's. That gets me 10 x's in total. Then I have 49 minus 34. That's 15. So there is my x function. All right, my g function, g of, and then whatever we plug in, what does g do? G is going to multiply the input by 3 and then subtract 5. And it's going to take the input, subtract 4, and then do that division. Fine. So if my input is x divided by 2, then I have to do all that. Okay, fine. Let's go ahead and do that. That's a little bit gross because 3 isn't going to cancel with the 2 at all. Something I'm going to do. So if I multiply by 1, I don't change anything. Yeah? Right? If I have 3 times 1, it's still 3. But this is a sneaky number 1, right? It makes things look different. Really, the way we use this is like saying that 6 over 2 is the same as 3. And one way you can see that is because 6 is 3 times 2. And anyway, what I'm going to do is I'm going to multiply and divide by 2. And on top, I have to distribute. And on bottom, I have to distribute. Okay? And so what happens on top? I have 3x minus 5. Oh, nope, lies. Minus 10, because 2 times 5 is 10. Whereas 2 times x over 2, 2 times x over 2 is just x, right? And there's also that 3. Okay. And on bottom, the x over 2 cancels with the 2, and I have minus 8. And already this is looking a lot better, and I don't think we can clean it up any more than that. Yeah, we really can't. So I'll go ahead and enter these, just because in case I made any small mistake, I'll experience the headache that is online math homework just to be in there with you guys. So, okay, we have x squared plus 10x plus 15. And here we're going to need division. We have 3x minus 10 over x minus 8. Let's check. Voila, right? Okay, so I really don't want to try another because it takes a little bit of time, and this looks very similar. So what else do we have here? Again, kind of same idea. So yeah. Okay, tell you what, I'll do this one. So I imagine you might want a couple more examples. All right, so f of 5 over x is 5 over x times 3 plus 7 over 6 times 5 over x plus 2. And to clear these denominators, what's the trick? I just multiply and divide by the same thing. And now I have to distribute on top. And so when I do that, 3 and 5 is 15. The x over x cancels. And I have 7x. And distribute. The x's cancel. 6 times 5 is 30. And I have 2x. So that's what I would input. There's really no way to clean that up more. Okay, g of x minus 3 is the square root of x minus 3 squared minus 9 times x minus 3. Okay, so that's the square root of, and now remember you have to actually FOIL this, right? So x minus 3 times x minus 3, and so then you're going to get x squared minus 6x plus 9. Then I'm going to do this one. I have minus 9x plus 27. Okay, fine. And so can we clean that up at all? We have x squared minus 6 minus 9 is minus 15x. Plus that is plus 36. Yep, that all looks good. Um, does this have a perfect square in it? 6 and 7? No, it really doesn't. Okay, so then those are probably your answers. So then I would just leave it like that. All right, let's see what else we have. Okay, domain of a rational function, excluded values. Wonderful. Let's take a peek. All right, so this is one of the things where when I was designing this, I actually don't have too much control in the sense of I can put down what I want you all to do and what makes sense as a flow to me. And then Alex says, no, they also have to do this. So if it were up to me, I wouldn't have you do this until you know how to factor quadratics, which does show up in the B modules. Um, so it's the B5 module. We get into the quadratics and how to factor them. And so that's why I have all the B modules unlocked, is you can go practice factoring if you want. I will show you how to do this without factoring though as well. We're just going to use Desmos. But um, I'll also talk a little bit about factoring. So, okay, we need to find the domain of this. So previously on domains, I told you that domain of a negative is no good. Okay, we're not allowed to do that. And so when you have the square, sorry, domain of a negative, the square root of a negative is no good. So when you have the square root of stuff, then you have to set the stuff to be bigger or equal to 0. Okay. And so we saw that with, like, for example, x minus 3. If that was your stuff, then x minus 3 has to be bigger than 0. Okay. That's one of the rules. Similarly, what you're not allowed to do is divide by 0. So I don't care what's up top. It can be whatever you want. Okay. Sometimes we use a star in math to mean it can be whatever you want. You have stuff in the denominator, and that's what I want us to focus on. Oh, fully charged. Nice. So we need the stuff in the denominator to not equal 0. So let's see what I mean. So I have x squared minus 10x plus 9. That's not allowed to equal 0. I said 0, I wrote 9. It's not allowed to equal 0. Okay, so that's telling us the x's that are not allowed. The x's that are not allowed are the ones that make this 0. And sort of by inspection, you can see that x equals 1 would make this 0, right? Because I would have a 1 plus a 9 minus a 10. I would get 0. Um, And actually, this can help us factor because this lets us know it now looks like x minus 1 times something else. And that something else needs to have a minus 9 here because when I multiply those two terms, that's how I get this. So I guess that's my factored form. So oops, the other bad spot is positive 9 because those are the two numbers where if you plug in 1 or if you plug in 9, then you would get 0, right? But we don't want to be 0, so we're not allowed to be yes. Okay, find all values of x that are not in the domain. It's 1 and 9. But I did say I'd show you how to do this with just graphing. So let's go to Desmos. Okay, cool. Yep, yep. And let's just enter this quadratic, okay? So I have x squared minus 10x plus 9. And then you can just see, okay, when is it 0? It's 0 when x is 9, and it's 0 when x is 1. Okay. So those are the two values that make it 0. Those are the two values you exclude. Okay, so you don't need to know how to factor. You can just put it in to Desmos and just find when is this equal to 0, and those are your bad spots. Okay. So let's try another. And again, the numerator doesn't matter at all. So here I have x squared minus 3x minus 40. Is there a quick answer? I'm gonna plug in, what does 5 do? Yeah, 5 would work. But let's see it in Desmos. So we have x squared minus 3x minus 40. And oh, maybe 5 doesn't work. So x equals, oh, if this was 0, then x would be 8, and x would be -5. Oh, so -5 works. That's close. But if it's not allowed to be 0, then you better not be that, right? So that's how we find our bad spots. Here I'd enter the 8 and the -5 because we want to know what's not allowed. See that capital letter not? Okay, whatever. That's how to do that. Where are we here? So we had domain of rational. Yes, finding values, functions, increase, decrease from the graph. Sure, I think this one will be really easy. So if we look from left to right, uh, then if the vertical isn't changing at all, it's constant. So from A to B, we're constant. If you go uphill as you travel from left to right, that is increasing. And then we're constant again. There's no change from C to D. And if you go downhill, that's decreasing. Okay. So whenever we say increase and decreasing, we always mean from left to right. And if something is constant, it means it's not changing. Okay, cool. Let's try another. Again, this is going to go fast, right? So from A to B, we're decreasing. From B to C, we're constant. There we go. From C to D, we're increasing. And then we're constant again. That's literally it. I have total faith in you all. Okay. Okay, sure. Some difference in product of two functions. Okay, fine. Let's take a peek at that. So you can multiply, subtract, add, divide. You can treat functions like numbers because at the end of the day, um, when we write r of x is equal to x plus 2, you're putting a number in here, right? Maybe it's 3. And so then a number is what comes out. 3 plus 2 is 5, right? So I can treat r of x the same way I treat x plus 2 and vice versa. And so if I say, okay, do r times s evaluated on x, what they mean is r of x times s of x. And what that means is x plus 2 times 4x squared. Okay. So you have to distribute this and kind of simplify it. What does it become? It's 4x cubed plus 8x squared. Okay. So that would be the first blank. Um, it's really not bad. Same thing. So like r minus s of x, what that means is r of x minus s of x. So what is that? It's x plus 2 minus 4x squared. That's it. Like you can reorder it, but at the end of the day, this is your answer, right? And then same thing for plus, right? I could have said like plus minus, plus minus, plus minus. It works the same. So that's all that's going on there. Some difference. Introduction to composition to functions. Okay, so now we're getting into, so composition is a big deal. Okay, this is a big, big deal. Um, it'll be showing up all throughout the course. It's already shown up, right? When we had to do stuff like f of even x plus h, which I know everyone loved that, but f of x plus 2 or g of 2 over x, we've already seen composition where there's a function inside a function. Okay, we do something to the input before applying the function. So anyway, what this is saying, there's a couple of ways we can talk about composition. So the way I like, even though it takes up the most room, is, we won't do the way I like first. We'll do my second most favorite way. So we have S of T of 2. Okay, so we're going to work from the inside out. So the first thing we're going to do is figure out what is T of 2. So this is S of, and T of 2, well, if I plug in 2 to T, I have minus 2 minus 2, right? You see my T function there? So this is S of minus 4. And what's S of minus 4? It's minus 2 times minus 4 minus 4. That's 8 minus 4. My answer is 4. Okay. So the final answer is 4. This works. If this makes sense, just do it this way. It's fine. Um, the way that I like to do it is with drawing sort of arrows. This is your first input, and then we need to apply t. So what does t do to that? It makes it -4. Um, I'm just computing this, right? I'm plugging in 2 into my t function, and then I'm putting down my output, and that becomes the input into S. So what does that do? That'll get us +4. Um, there are many ways that I could write this, right? I could talk about like the t at 2. I could actually put the computation here and then I'll go here. Whatever. Just do inside, unpack, and unpack some more. Let's try another, just get more practice with this. So u of w of 3. Okay, fine. So what's w of 3? Let's see. It looks like it's going to be -3 minus 1. It looks like it's going to be -4 again. What are the odds? And what's u of -4? It's 3 times -4 plus 5. That's -12 plus 5. That's -7. Okay, so there's our answer. All right, so that's some composition stuff. Composition functions basics. So now we're probably going to do it with just variables. Oh, nope, we still have this stuff. All right, fine, whatever. Okay, so see how they wrote a little circle R? Um, this is just another way to write composition. So what this means, so the definition is Q of R of 4. So it's actually what we just saw. Okay, it's just another way to write it. But that little circle is called a composition circle. So we need to do R first. So we're going to do 4 squared minus 1. 16 minus 1 is 15. So this is Q of 15. And then that's going to be -2 times 15 plus 2. That's -30 plus 2 is -28. Okay. So anyway, if we change the order, so if I have R after Q on 4, again, this is just R of Q of 4. So this is R of, so what's Q of 4? If I plug in 4 to, oh, did I do it the wrong way? No, I didn't. Okay. Q of 4 is -8 plus 2 is -6. And R of that is going to be -6 squared minus 1 is 35. Okay, so these are different values, right? That it doesn't commute. That's what that's called. You can't switch it and get the same answer. I mean, sometimes you can, but whatever. Not with this. Okay, so that's the same as what we just saw. Just new notation, right? They introduced circle notation. Almost done with B2, and then we'll call it good for this video. And then I'll do one for your homework. Composition of function with itself. Oh, I do love this. This is near and dear to every mathematician's heart. We love it so much. So I have this function h. Oh, what a function. You fun. Okay, anyway. This is 3 over 5x. And so if I do h on h of x, well, h does 3 over 5. And then what's going to go here is h of x, which is 3 over 5x. Okay. Do you see how that worked, or did I could try and write this in a few different ways. H of blah is 3 over 5 times blah. And so if I put an h of x in here, well, then that's like putting a 3 over 5x in here. So I better put that in here, 3 over 5x. Anyway, we can clean this up a little bit. So let's go through the algebra. 5 times 3 over 5x is, those cancel, 3 over x. Okay. Truly, I don't know how you were taught fractions. Students overthink them. You just multiply straight across. That's how fractions work. You just multiply straight across. So this 5, if you want to think of it as 5 over 1, that's fine, whatever. In my mind, it's in the numerator. I don't need to write over 1. You always just multiply straight across. That's how multiplication works. It's very nice. So that gets us to this stage, 3 over 3 over x. Okay, and here's the thing. Another thing, I bet you know, if I have a and I divide it by 2, you could also write this as a times a half. Okay. Now, if you didn't know that, you should maybe come talk to me about it or look into it or something. But if most students are pretty comfortable with this, and yet those same students can sometimes be less comfortable with this fact. But the same thing happened here. See, division by 2 is not actually what's going on. What's going on is multiplication by the multiplicative inverse of 2. Wow, what a mouthful. We tend to just say the reciprocal of 2. But division doesn't exist. Division, when we write that, when we write a symbol like this, it's shorthand. It means multiply by this reciprocal number, which is called the multiplicative inverse because 2 times 1/2 equals 1. So the multiplication by half undid multiplication by 2. You get back to just 1, which is the identity in multiplication land. Anyway, the multiplicative inverse of a half is 2. This is the same thing is happening in both of these equalities, right? So I'm here, this is 3 times, and then I look at this and I say, x over 3. Oh, look at that, those are gone. I get x, okay? So what's kind of cool about this is h is its own inverse function. So if I do h twice, it's like I did nothing at all. And let me make that make more sense. It's going a little bit beyond what we need to go, but it'll eventually show up, which is why I'm taking the time to just talk about it now. So if I start with any number I want, so for example, 7, okay, and I apply h to it. So I have to do 3 over 5 times 7. This is 3 over 35. Okay, fine. There's h. And now if I apply h to that, I claim I'll get 7. Okay? Because if you do h twice, no matter what you put in, x, apparently you just get x out. So let's see. So I need to do 3 divided by 5 times 3 over 35, right? What I'm doing is I'm computing h of 3 over 35. I'm feeding this into h, and I want to show you that we get 7. Okay. Okay, well, this is 3 over, and then 5 and 35, that's going to reduce to be a 1 over 7. And then we have to flip 7 over 3, and those go away, and you get 7. Right? I already knew this was going to happen because we did it in the general case. So we would say h is its own inverse because if you do it twice, it undoes itself. Whatever you started with is what you end with. Another example of a function that's its own inverse, so like f of x equals 1 over x, classic, right? Because if I do f of x, this is, well, I guess the way I taught it before was I said do the inside first, and then what does f do to its input? It flips it. Let's just be back to x. Anyway, I'm getting off topic now. So, oh, the f I just wrote is not the homework f. That was me being lazy coming up from there. So let's do the homework one. So f of x is 6x minus 3. Okay, fine. What is f of x? Well, it's 6 of f of x minus 3. And what's f of x? It's 6x minus 3. Okay, so we can clean this up. It's 36x minus 18 minus 3, which is 36x minus 21. Okay. Anyway, so that's function composition with itself. All right, 4 more to go. Expressing a function as a composition of 2 functions. Wonderful. This is a very useful skill if you have to go on and take calculus. You're going to use this all the time. So h of x, it's the square root of stuff. And what's it the square root of? It's the square root of 7x squared minus 9. Okay, so why do I write it like this? Because what I want you to notice, so if we're going to write this as f of g of x, I claim that my f function, maybe I'll just write it like this, my f function is the square root function. And then my g function is 7x squared minus 9. And so now, if you do f of g of x, this is the square root of g of x, the square root of 7x squared minus 9. So my function h can be broken down into, if I first do g, so now I have 7x squared minus 9, and then I do f, and now I have the square root of 7x squared minus 9. Going from here to here, that's the same as doing h. Okay. Let's try another. Okay. Interesting, interesting, interesting. This is kind of fun. Um, so uh, I first do G, and then I do F, and my end result is going to look like 5 times the cube root of x minus 2. And sort of what stands out to me is I have 5 times something minus 2. And so if my f of x is 5 times something minus 2, and my g of x is the cube root of x, well then, f of g of x is 5 times the cube root of x minus 2, and I get exactly what I want, right? So my f of x is 5x minus 2, my g of x is the cube root of x. And now when you do f of g of x, you'll get h of x, just like what you need. Let's try another. Okay, so f is last, g is first. My f of x, the last thing that happens is a cube root. Oop, sorry. The first thing that happens is this 7 minus 2x. And now if I do f of g of x, this is the cube root of g of x. This is the cube roots of 7 minus 2x. Okay. So anyway, there's my f and my g. Let's try another. And do another. Whatever. They're all kind of the same. Um, yeah, here we go. Well, no, whatever. I beat that to death. Okay, expression of functions. Sure. Composition two functions, domain and range. Okay, cool. So now we're going to level up a bit and we're going to start talking about domain and range. All right, domain of f after g, right? So we need to remember, despite reading left to right, so I read f compose g, g happens first, f happens second, okay? So domain of g is 1, 7, 8, 9, and g sends 1 to 0, it sends 7 and 8 to 4, and it sends 9 to 1. And so this is my G column. Now my F column will send 0 to 0. It will send 4 to 0 as well, but it never touches 1. So what does that mean? What does that mean? Does that mean you're not in the domain, Mr. 9? Because, yes, indeed, yes. Okay, so I think these three numbers are the domain of F after G. You see, 9, it's probably not in the domain because if I were to ask someone to compute f of g of 9, then that's like asking them to compute f of 1. And if you look at your function f, I don't know what f of 1 is. It doesn't exist because 1's not in the domain of f. So we have to not allow ourselves to get there. So, okay, let's write this out. So this is 1, 7, 8. Now let's try it the other way around. So now we're going to do, go away. Now we're going to do G after F, or no, range of, oh, I should have erased that. Let's put this back. The range, okay, so where do we end up? I think we just, we just end up at 0. That's the only thing in our range. Okay, thank you. 0, let's check. There we go, cool. Let's try another. I imagine this might take a little bit of practice. Okay. So we've got 2, 4, 6, 7, 8, 9. 2, 4, 6, 7, 8, 9. And we've got 0, 2, 6, 7, 8, 9. Okay, 2 goes to 2, 4 goes to 7, 6 goes to 9, 7 goes to 0, 8 goes to 6, 9 goes to 8. Okay, what about F? F will send 2 to 3. This is G, there's F. And yes, okay. F will send 2 to 3. F will send 3 to 5. There is no 3 here. Okay. Um, in fact, okay, F will move 6. It'll send 6 to a 2. It'll send 7 to a 2. Okay. It'll send 8 to a 3. Okay, and I guess that's it. So if I look at, so for example, this 9 is not gonna be in the domain of F, so we can take out this 6. It's not gonna be in the domain here. Similarly, this 0 is not in the domain of F, so we can take out this 7. It's not gonna work. I think everything else is okay. So if I go here, we're gonna hit our set button, and we have 2, 4, 8, and 9. And then for the range, that's the values all the way over here. On this end, we have 2 and 3. So set button, 2 and 3. Check. Okay, there we go. All right. Almost done. Composition is two function advanced. All right, and then we'll do word problem. Cool. Wonderful. Yes, I'm so glad we have this. Okay, so we're going to do G after H. G compose H on X. So that's fine. We could also write it like this, G of H of X. And previously I've shown us unpacking from the inside out. So that would be like doing this. G of X minus 4 equals the square root of 5x minus 4 plus 30. You could also unpack from the outside in. So I could write out what G does. G is the square root of 5, and then I'd say times H of X plus 30, right? Because my input is H of X, so there it is. And you can see, like, it's just, it doesn't matter where you unpack it, right? At any point in time, we can unpack H of X. We just have to be consistent. Okay, so our goal is to find the domain of this composition, which is to say the domain of this function here. That's where we end up when we unpack everything. And remember, if I have the square root of stuff, then I need the stuff to be bigger or equal to 0. So I take everything in my square root, which let's go ahead and just clean this up a little bit. So this is 5x minus 20 plus 30. Oh, well, let's clean that up a bit. That's 5x plus 10. That has to be bigger or equal to 0. And so what does that say? It says 5x is bigger than or equal to minus 10. And if we divide by 5, that says x is bigger or equal to minus 2. Okay, that's our domain. So let's enter this all in. This is the square root of, and if I clean that up, it's 5x plus 10. And the domain of this, I need x to be bigger or equal. There we go. So you could possibly be as small as -2, or you're bigger. Okay, there we go. Careful, finish your work. Don't tell me what to do. Find the composition, specify its domain, using interval notation. I did all that. X is bigger than or equal to -2, yes. And this would be a minus 20, and a plus 30 is a plus 10. Am I missing something? I don't see that I'm missing anything. Yeah, okay, that was weird. I don't know. Alex is weird. I hate it. Okay, I think they're all going to be pretty similar. Okay, sure. So we'll do this one. So now we have a rational function. So can't take the square root of negative, can't divide by 0. Them's the rules. No, I can get more into it. Truly, it's not arbitrary. Okay, so we need to look at f of g of x. So this is going to be g of x plus 4 over g of x minus 5. So this is going to be 2x plus 3 plus 4 over 2x plus 3 minus 5. So it's going to be 2x plus 7 over 2x minus 2. Okay, there's our function expression. And we need the bottom, 2x minus 2, to not equal 0. Okay, you can solve for x the same way you normally would, and you just leave that symbol there. So for example, 2x is not allowed to equal 2. I add 2 to both sides. And then I divide by 2. X is not allowed to equal 1. Okay, So the domain is everything that's not x equals 1. And now we get to sort of a new notation thing in this class. So if x is not 1, you can be any number less than 1, but don't you dare touch 1, right? So that's it's a curvy bracket. Or, and so the way I express this idea of or in mathematics is with it's called a union symbol, but it's with this like sort of letter U looking thing. Or you could be bigger than 1. Okay, this is my domain. So I'm glad that we did this problem as an example. So let's go ahead and write out what this is. This is 2x plus 7 over 2x minus 2. And then the domain, we have this, which is negative infinity to 1, union, interval, 1 to infinity. Be careful. I did finish my work. How about you go fuck yourself, Alex? All right, there we go. Cool. Let's try another. Okay, and so then f of, sure, whatever. No, I think actually I'm good with this one because there's just going to be a square root. You just make it positive, but maybe I'll help you all out with the, so we have f of g of x, and so this is 2 times g of x minus 4, plus 1. And so you need this to be non-negative. So x can be bigger before, whatever. All right, that's good for that. Last one, and we're done with the B2s. Yay. And I'll do a video for your homework. The braking distance in meters given a velocity is given by this. Okay, so the braking distance, whatever, I don't want to write it. We just might need this. V squared over 26, fine. The car's velocity after starting is given by that. Okay, so the velocity is a function of time. They call it b to try and trick you, but v, the velocity, is 3 times time. And so what we're going to have to do is 3 times time squared over 26. That's going to be this final composition. But let's just read out the stupid problem. Okay, so the braking distance for a certain car moving at velocity v is given by that. The car's velocity after t seconds is given by that. Write a formula for the braking distance after t seconds. And so that's going to be this composition thing that I just did. Because if v is equal to 3t, and if this is how long it takes you to brake, you just compose them. This is, if I was to write it all fancy like, then I'd have d of b of t. All right, that's what I did. And so what's that going to be? It's 9t squared over 26. Fine, 9t squared over 26. Yeah, whatever. Let's try another. They name these things silly to try and trick you, but you just kind of want to let like the objects guide your thinking. So temperature in degrees Fahrenheit in terms of Celsius is that. Okay, fine. And the temperature in degrees Celsius in terms of Kelvin is that. So all right. Degrees Fahrenheit in terms of Celsius temperature D. So oh, I wish I could, I mean, I guess I could do this. We'll go here, and then I can sort of highlight some stuff. So in terms of Celsius temperature D, they're letting you know the letter D represents Celsius temperature, right? So really what I'd want to say is that F as a function of C. That makes more sense to me. I know that I input Celsius, I output Fahrenheit. Okay. And then it's 9/5 C plus 32. So anyway, knowing that, let me just rewrite this as F of C is equal to 9/5 C plus 32. And now let's look at this other one. The temperature C in degrees Celsius in terms of Kelvin, okay, so C is a function of K. I'm not going to use V because I'm not going to try and trick you. I'm going to use K for Kelvin, is equal to K minus 273, right? That's not right. It should be plus, right? Because 0 Kelvin is negative. Oh, no, that is right. Oh, wow. 0 Kelvin is negative 273.15 degrees Celsius, right? Okay, so F of C of K. So this is going from Kelvin all the way to Fahrenheit. This is 9/5 times k minus 273 plus 32. Okay. Boop, there we go. Yeah, that's all we need to do for this. So, okay. Um, that's it for B1 and B2. See y'all in the next video. Let's